Something unusual has been unfolding with the interstellar object 3I Atlas ever since it first entered the solar system. What initially appeared to be a fairly predictable interstellar comet has gradually turned into a puzzle, with new observations suggesting its motion may not be behaving the way scientists originally expected. Early trajectory models created by the NASA Jet Propulsion Laboratory assumed that the object's path could be explained by two primary forces. The first is gravity, mainly from the Sun and to a lesser extent from the planets. The second is what astronomers call non-gravitational acceleration, a subtle push created when gases erupt from the surface of a comet as sunlight heats its frozen materials. These jets act like tiny thrusters, slightly altering the object's speed and direction. For months, scientists believed they had a solid understanding of how these forces were affecting 3I Atlas. Using observational data gathered by telescopes across the world and in orbit, researchers calculated the object's velocity, acceleration, and projected path as it continued its journey through the solar system. The expectation was that its trajectory would remain largely predictable once these influences were accounted for. But a newer analysis, based on hundreds of observations, has suggested that one of the key assumptions about the object's motion may not be correct. The issue does not appear to be the total amount of non-gravitational acceleration acting on the object. Instead, the difference lies in the direction of that acceleration. Earlier models assumed that most of the extra push came from gas escaping the sunlit side of the object. When sunlight heats the surface of a comet, ice turns directly into gas and erupts outward. Because this process happens primarily on the side facing the Sun, the resulting force should push the comet mostly away from the Sun, producing what astronomers describe as a radial acceleration. However, the new analysis suggests that the situation may be more complicated. Instead of being pushed mostly outward from the Sun, the object appears to be experiencing a sideways force as well. In other words, the acceleration may have a strong transverse component rather than being purely radial. This difference might seem minor, but even extremely small forces can produce significant changes in the path of an object traveling through space over long periods of time. The acceleration being discussed is incredibly small, measured in micrometers per second squared. Yet when that tiny force acts continuously for weeks or months, it can shift the object's position by thousands of kilometers. That small change in position could become important because of the object's upcoming passage near the orbit of Jupiter. Jupiter is the most massive planet in the solar system, and its gravitational influence extends far beyond the visible planet itself. Surrounding it is a region known as the Hill sphere, where the planet's gravity can begin to dominate the motion of nearby objects. If 3I Atlas passes close enough to this region, Jupiter's gravity could alter the object's trajectory. Even a slight adjustment in distance could determine whether the object remains primarily under the Sun's gravitational influence or briefly falls under Jupiter's control before continuing on its way. The idea of a large interstellar object interacting with Jupiter's gravitational field has sparked a range of questions about what might happen next. One possibility is that the planet could deflect the object slightly, bending its path as it leaves the solar system. Another possibility, sometimes suggested in more speculative discussions, is whether the object could somehow be captured by Jupiter and become a new moon. However, the physics involved make that scenario extremely unlikely. Objects moving through the solar system at interstellar speeds carry enormous kinetic energy. In order for Jupiter to capture something like 3I Atlas permanently, the object would need to lose a tremendous amount of velocity. Without some form of dramatic braking force, it would simply pass through the planet's gravitational influence and continue on its way. Estimates suggest the object may be roughly 2.6 kilometers in diameter, giving it an enormous mass if it is primarily composed of ice and rock like a typical comet. Slowing something that large by the tens of kilometers per second required for gravitational capture would demand energy on a scale that far exceeds anything naturally available during a brief planetary flyby. As a result, most realistic scenarios involve only modest changes to the object's path, rather than any kind of capture event. Jupiter could bend the trajectory slightly, perhaps sending the object out of the solar system along a somewhat different route than originally predicted, but the overall outcome would likely remain the same. The object would continue traveling through interstellar space. While the trajectory question is still being studied, observations of the object itself have revealed several intriguing features. High-resolution images taken after the object passed closest to the Sun showed evidence of multiple jets erupting from its surface. These jets appear to be relatively narrow and localized, rather than coming from a uniform layer across the entire surface. The presence of distinct jets can help explain the sideways acceleration detected in the new analysis. If several jets are active at different locations across the object's surface, they may produce forces that do not perfectly cancel out. Instead of pushing the object directly away from the Sun, the combined effect could generate a sideways component to the motion. Images from the Hubble Space Telescope also suggest that the object rotates with a period of about 7 hours. As it spins, the orientation of the jets changes relative to the Sun. This rotation can cause the direction of the outgassing forces to shift over time, further complicating the object's motion. Another surprising discovery involves the chemical composition of the gases released from the object. Early observations indicated that the object was emitting large amounts of carbon dioxide and carbon monoxide, along with relatively small quantities of water vapor. This composition was unusual compared with many comets observed within our solar system. Later observations, made with the James Webb Space Telescope, detected something new: methane appearing in the cloud of gas surrounding the object. What made this particularly puzzling was that methane had not been detected earlier, even though it is a highly volatile substance that normally begins evaporating at very low temperatures. One possible explanation is that the outer layers of the object were depleted of methane long before it reached our solar system. If the object experienced intense heating in its original planetary system before being ejected into interstellar space, much of the methane near the surface might have already escaped. In that scenario, methane would remain trapped deeper inside the object. When the comet passed close to the Sun, heat could penetrate the interior and trigger the release of methane from these deeper layers. That delayed outgassing would explain why methane appeared later in the observations rather than during the object's initial approach. However, the chemical story is not entirely straightforward. Carbon monoxide, which is even more volatile than methane, was detected early in the object's approach. If the surface had already been stripped of volatile substances during earlier heating events, scientists would expect carbon monoxide to be depleted as well. Yet, it was present in significant quantities. This apparent contradiction has led researchers to consider alternative explanations for the object's internal structure and history. Some have suggested that the body might resemble certain distant objects found in the outer regions of our own solar system, where unusual mixtures of volatile materials can persist under specific conditions. Whatever the explanation turns out to be, the combination of unusual chemistry, complex jet activity, and subtle trajectory changes has made 3I Atlas one of the most intriguing interstellar visitors ever observed. Interstellar objects are already rare discoveries. Only a handful have been detected passing through the solar system, and each one offers a rare glimpse into materials formed around other stars. Because they originate in distant planetary systems, they carry chemical and physical signatures that may differ from objects formed around our own Sun. Every new observation helps scientists refine their understanding of how such bodies behave and how they evolve during their journeys between stars. The case of 3I Atlas demonstrates just how complex these objects can be. A tiny imbalance in the direction of gas jets can alter a trajectory enough to change whether the object experiences a gravitational encounter with a giant planet. Subtle chemical signatures can reveal clues about environments that existed in another solar system billions of years ago. Even a small change in the direction of a jet can affect how astronomers model the motion of the entire object. As 3I Atlas continues its path outward, astronomers will keep tracking its position and studying its behavior. Each observation will add another piece to the puzzle, helping scientists determine exactly how its motion is evolving and how its interaction with the Sun and the planets may shape its final exit from the solar system. Whether Jupiter ultimately nudges the object onto a slightly different path, or the comet simply passes by unaffected, the encounter represents one more opportunity to study a traveler from another star system while it briefly crosses our cosmic neighborhood.